Come and stand here, Mauro, if you want to start.
Hey everybody, welcome to the public defense in the computer and information science of Tobias Olsson. So let me start by introducing the candidate. Tobias has been with us at Linnaeus University since a long time. I just discovered that. He joined the LNU in 2002 as a lecturer. And then started his PhD in 2010, right?
Something about that.
Yeah, under the supervision of Morgan Eriksson as a main supervisor, and Anna Winkvist and Velf Löv as assistant supervisor. Today's Tobias finally reached the destination, hopefully, and will defend his PhD thesis entitled Incremental Clustering of Source Code, a Machine Learning Approach. Together with Tobias, we also have the opponent, Sebastian Herold, who is Associate Professor at Karlstad University in Sweden. He joined us via Zoom. Hi, Sebastian, welcome. Sebastian is a well-known member of the software engineering community, and he's also an experienced researcher with special interest in using AI techniques for software design and for improving software quality, right? So Sebastian's research interests are very close to the Tobias one, as they attack the same problem, but with, let's say, two different methods for solving it. Then I would expect a really interesting discussion today. Then we also have the evaluation committee members. We have Michel Choudron here, attending here in Kalmar, professor at Eindhoven University of Technology from Netherlands. Then we have Raffaella Mirandola, associate professor at Politecnico di Milano, Italy. Hi, Raffaella, welcome. And finally, we have Jim Buckley, associate professor at the University of Limerick in Ireland. Hi, Jim, welcome. So the research done by Tobias has been performed here at the Linnaeus University, as you could imagine. Now we start the dissertation. Tobias will give a short introduction about the work done in these years. Then the opponent will discuss the dissertation with the candidate. Then we will also give the possibility to the evaluation committees to make some comments and questions to the candidate. And finally, also the audience will be allowed to make questions to Tobias. So then the stage is yours, Tobias. Good luck.
Thank you very much. So I hope my presentation will show up now. Is it showing or not?
This feature
Testa igen. There we go. All right, good start. So thank you very much, Mauro. And I will be presenting my work, Incremental Clustering of Source Code, a Machine Learning Approach. And to start things off, let's take a look at how software could actually look in a fairly evolved system at the source code level. So we see this mess of lines going up and down and left and right, and it looks quite messy. So understanding a piece of software from this perspective is quite hard. And this is something that actually happens a lot in software as it evolves. The source code becomes a mess. So then we can look at source code at a more higher level, the architectural level. And if we take a look at well-evolved pieces of source code, software systems, we see kind of like the same pattern. We have a lot of parts of the software system, but they are more or less all interconnected. So looking at an implemented architecture does not really help that much. We can take one step further in abstraction and take a look at services-based systems. But again, we see kind of like this same mess of parts that are interconnected and really hard for anyone to understand and try to make sense out of. And this is a well-known problem in software development, that over time, with the evolution of the software, the complexity often rises very sharply. And if you don't actively do something about that. So maybe it's not that odd that our houses of software are not always that easy to change. And why does it take so long for something new to be added? Or why does it take so long for a problem to be fixed? However, we can take a look at how we actually would like this software to look. And then we take a look at an intended architecture instead. This is a picture over a software system that we can actually make sense of and try to reason about. We can probably understand most of this, even if we don't really know what this software system is about. So having this intended architecture is then vital to our actual understanding of how we want the software to work and how we want the software to be structured. The problem is then that in reality, the software systems look like this big mess of things. So we would like to have a way to check the architectural consistency so that developers actually put the software parts in the correct boxes and they depend on each other in the correct way, as we have intended them to do. So we try to divide the source code into these nice modules, and we define these allowed relationships between these modules. And by doing so, we can easier divide the labor, we can reuse parts, we can analyze performance, and we can support the development in a much better way. And hopefully our window will be much faster to be added. So we need to manage all of these dependencies, or they will turn into this big yarn of mess. So the most popular, or maybe least unpopular technique, is to use reflection modeling. And then we can compare our intended architecture with an actual implemented architecture. The problem is, of course, then that all of the parts in the software systems need to be put into one of these boxes. And basically, that is what I have been working with. So this problem is called mapping or orphan adoption. Orphan adoption is probably the worst name ever, but yeah, what you're gonna do. So the idea is that we would like to take one part of this software and put it in the correct box as it was intended, or another part and put in another box. And then we can do analysis based on this. But as you can imagine, there are a lot of small parts of software here, and putting them in the correct box will take a lot of time for a human to do. So we want semi-automatic techniques, or as automatic as possible at least. And there has been some work in this area before. From 97, we have this orphan adoption technique, where Serpos et al. Used an algorithm to try to do this, and they defined different criteria for how things should be mapped into the correct box. We have Hug Me by Crystal et al. That also defines an algorithm to do this with the support of a human involved. So the machine does part of the work, and then a human can do part of the work, and then the machine can use the information that the human has provided to improve mappings even more. And we have InMap by Sinkala et al. In 2021 that uses a recommendation system that recommends mappings for a user that he can reject or accept. I have focused on the Hug Me algorithm or the Hug Me method to do this. And in Hug Me, you assume an initial set. So we have some parts already mapped, but we have maybe a lot of new parts or just a few new parts that need to be mapped. And the idea is then that using the information that already exists, we try to make an intelligent choice of a new mapping. And if this choice is good enough or particularly outstanding, the mapping is performed automatically. Otherwise, we let the human decide, or we delay this mapping to another iteration of this algorithm. So when we have more information, we can maybe do the automatic mapping. So as we map both automatically and manually, this initial set grows, and we have more information to learn from when using Hug Me. So this could be an example of that. So we have a new orphan here called string change, a source code file that should be mapped to one of the architectural modules, graphical user interface or logic. And we can see that we have some information here that we could use. We could, for example, count the dependencies that we see, and we could say that, string change has many dependencies to stuff in logic, so we should put string change in the logic box. Or we could say that, no, that's not correct, because then we would violate this architectural dependency that we have created. So it's better to put graphical string change in the graphical user interface module. Or we could actually take a look at the name here and say, this is named change. We seem to have stuff connected to change by looking at the names of the already mapped items, and see that, this indicates that string change should be mapped to the graphical user interface. So this is basically how these mapping techniques work. So to perform this automatic mapping, we have different ways of computing the similarity or the attraction to one of these modules. And Crystal et al. Used actually two methods, but one was very much better. So this is the one that I will be talking about. It's called count attract. And basically what that does is this counting of the dependencies. So it tries to count dependencies between the orphan and the modules and make an intelligent choice based on that. And Bittencourt and al. Also worked with information retrieval techniques, which tries to use this semantic information in the source code. For example, the names of the files. And we could see that we had this change word, and maybe that indicates also some type of information that we can use. So basically, count attract uses this syntactical information, parsing the source code, finding out the dependencies to other parts of the source code. And we have these information retrieval techniques that uses the cosine distance or latent semantic indexing to compute an attraction. And we can compare these different types of techniques with each other using a performance metric, and we use the F1 score of precision and recall, which is common in these types of techniques. So we try to find out some ratios of how good is this algorithm and compute a number to indicate this goodness. So this was basically the background. Compared to this count attract, we saw that we had an idea that, well, if we feed this algorithm a good set of source code, maybe the result would be better than if we just feed it a random set of source code. So we tried to find out a good set of source code, because then the human could map this good set and the algorithm would perform better than just having a random mapping. So this worked to some degree, but when we tried to generalize it, it could not really be generalized to different types of systems. And we tried to use different types of dependency metrics. For example, the fan out, counting the number of dependencies. And the idea was that, well, if the human maps the files that have a lot of dependencies to the correct modules, we can later then trust this information and use it to map much better automatically. But we also learned that the composition of this initial set is actually important, because different types of metrics gave us different results for different systems, but it was very hard to draw any general conclusions based on this. So the next step in this improvement of counter-tract was to try to use different types of dependency weights. So maybe we could assign different types of dependencies, because in object-oriented systems, we often have a rich set of dependencies, like method calls, we have attributes of different types, we use inheritance, we implement interfaces, and so on and so forth. And maybe this has some, could give us better hints if we maybe have a weight for inheritance. Inheritance is very important for this mapping. Then we should count that as something more important in our algorithm too. Or maybe if uniform weights are good enough, is there a difference here at all? So we tried to make a comparison in this area. Uniform weights, they are nice because they are simple. Everything is worth the same. So it's very, very convenient for a user, because there's no settings for a user to do here. Or we could maybe compute some simple metrics, a little bit like we did in our first approach. We could try to compute how many dependencies are internal to a module and how many dependencies go outside of the module. And we can compute a ratio here and try to give a clue on how important this metric actually is. How important is this dependency? Or finally, we could, of course, try to compute some type of optimal weights here. And we choose to use a genetic optimization algorithm to compute these optimal weights, because we thought that there's a fair chance that this will not be simple, but the dependency weights will influence each other, and it will be very hard to just guess or intuitively set them. So we need some way to really try to optimize them. So in our genetic algorithm, we then start off everything with 10 initial sets and a generation of randomly generated weights. And for each generation, we pick out the most fit individual by checking the winner of the F1, this F1 score that is calculated for each of these initial sets. And an individual A is better than, more fit than an individual B if it has a higher F1 score in a majority of these 10 initial sets that we have computed. And then we try to spawn new individuals based on a tournament selection and a uniform crossover. And we do a little bit of mutation also of these. So we tweak them a little bit, these dependency weights. And we also finally have that the most fit individual will survive for a little bit longer than a single generation only. So when executing an algorithm like this, you often get a lot of data, or rather a lot of different mappings that needs to be done. We did not expect a single optimal result here really. So we choose to just run this for 300 generations, because after that we couldn't really see any large changes in performance. But given this, 30 individuals in every generation, we have 10 initial sets, and we do this for 300 generations, and we do 90,000 mappings for 8 systems. So we end up in 720,000 mappings in total to compute these optimal weights. And that's about 200 days of execution time. And that's not fun to wait for and then realize that you have made a mistake and try to do it again. So we need some way to parallelize this. And that's also where genetic algorithms are quite good, because we can run every individual in parallel on different cores. And this could cut down our execution days to 9 days instead of probably something around 200 days. So we have a nice high-performance computing cloud to do that, and that's has been instrumental in this work. So what do we get then? What can we learn from this? Well, the first thing that we took a look at is this ant system and this teammate system. And when we do this ratio of the dependencies, we find that a dependency in these systems actually more often points outwards of a module than internal to a module. So they are not at all designed with this principle of trying to keep the dependencies overall inside of the modules. So that's an interesting finding. Another finding is that this inheritance, or in Java extends relationship, was deemed important by the optimized values in almost all of the cases, except for this Pro-M system, which is a little bit of an outlier, really, because that's really a well-designed system. And a little bit surprising is also that this method call relationship was not at all valued by the genetic algorithm for any of these systems. So method calls did not help us do this clustering at all for count-attract. And we could see some interesting patterns also. For example, in some systems, using the constructor calls, creating objects is important, and this could indicate that they have some type of special mechanism for creating objects like factory patterns or stuff like that. But the most interesting part is that some systems are overall not at all designed to be cohesive in general regarding every type of dependency. And that inheritance was very valued type of dependency in every system here. So that's kind of interesting. So now that we have the weights, the optimal weights, we can try to compare it with the uniform weights, or these semi-smart weights that we also had. And to do this, we have even more mappings to do. So in total, 1.2 million mappings were made to compute the performance of each of these techniques. And, well, maybe not that surprisingly, the optimal weights are good. They are better than the other two in every one of these cases. And if we took a look at the ant system that was not this cohesive design, the difference is indeed bigger. And we can also see that the other techniques actually decline in performance, because the more dependencies we add, the harder time it has actually to perform well. But in a system like JabRef, which is pretty well designed, there is a small difference between the optimal weights and non-optimal weights. So the problem then is, of course, that a human can never set these dependency weights to something that is reasonable. There's too many of them, and the weights are non-intuitive. So how can we get a good result from this for a new system? Hard problem, but we turned into machine learning to try to improve this situation. So the problem previously was that, well, we have more types of information that we would like to use. We would like to use these dependencies, but also the words that are actually in the source code. And we would like to have few parameters for the user to decide. So we decided to go for classification because we could regard the modules as classes, and then we had some information in each class, and that could help a machine learning algorithm to actually make this automatically. Problem is, of course, then how should we combine this dependency information with the word information, the words in the source code? How can we reduce the need for parameters? And what is actually the performance? Will it be better or not? And to solve the first problem, we found inspiration from a mapping session where we listened to an architect that said that in this module, it's common that we create objects in this other module, for example. So why not try to do this also for our algorithm? So in the code, we can find that class A depends on class B, but this is, of course, too specific because we cannot use that, so we need to abstract this to the modules instead. So if the class A is mapped to module A and class B is mapped to module B, we could instead say that classes in module A depends on classes in module B. And we can form that into a textual token, and then we can more easily combine it also with the text tokens from the source code itself, and we have one model for everything, so to speak. And we choose a multinomial naive Bayes technique, which is a fundamental text classification algorithm, machine learning algorithm. And one of the major advantages here is that it is good with small sets of data. So if we want to map an entire system from scratch, we don't want to need to be able to do a lot of work to create this initial set. We want it to be as small as possible because this is human work again. It's quite fast and it's easy to implement, and it's a good baseline technique. We did some tests with other techniques also, but we found out that naive Bayes was the way to go, at least from the data that we have. And we use these textual dependencies then to combine them with the text from the source code. And this can also be used actually in the information retrieval techniques that are already there. Then let's take a look at the comparison. Now that we have 4 different types of ways to compute the performance, we can take a look at which one is actually the best. And the technique that we have developed seems to be better in all of the cases. In some cases, well, maybe not by much. I think this well-designed ProN system is every technique performs quite well. But if we take a look at, for example, ANT, then that is not designed with these cohesiveness in mind, our technique actually outperforms the other by quite a fair amount. And this is also our technique called NB attract, and then we have the count attract with the optimized weights, and then we have IR attract and LSI attract. But it's interesting to see here that the combination of the learning of the weights and the information in the source code provides an advantage over just using the optimal weights. So this naming information is good for increasing performance even more. And if we look at a detailed view, we can again see that our technique to compute these attractions seems to outperform the other techniques in all of the different cases, and specifically over the whole size of this initial set. And this is important because maybe you have a situation where you don't want to map everything. You have already established a good mapping, and the system is maybe in development and you just add a few files. So it's good to have good performance at the end. And it's good, of course, to have good performance at the beginning because mapping from scratch is costly. Okay, so we now have a good way of doing mapping, but we still have this problem with the initial set. It would be interesting to have a fully automatic technique. While we have not achieved that perfectly, we have at least come a little bit on the way here. And that is by using some handcrafted keywords for every module. So looking at, for example, the module name, we can see that it corresponds often to parts of the source code that we could then use to create this initial map. And we constructed a proof of concept to do this, and we could find out that out of the 96 modules that we had, only 10 required a weighting of the keyword, so we could stress that something was a little bit more important. And 15 out of 96 needed multiple keywords. So if the structure is well made, there is a good chance that you can find nice keywords by looking at the source code structure. And these often map with the module names. And using this, we can then create this initial set, and then we can run the NB attract mapper on top of this. And then we can get quite good performance, actually. So this dotted line, the green dotted line, is when we have the keywords, and then we add NB attract on top. And for example, this blue, little bit more jagged line here is when we use a random initial set and try to map as good as possible using NB attract. One key part of this work has been to create an open source tool suite where we have this core of these algorithms that we have implemented. We have the attraction functions there. We have an engine to perform experiments. We can parse the bytecode of Java and extract information from it. We have a tool to create experiments visually and also assess experiment ideas quickly. And we have this tool to run several experiments in parallel. And finally, we also have built the genetic optimizer on top of this tool suite. All is well? Unfortunately not. There are still some hard cases in this mapping. And this is an interesting topic, but I will just do it quickly. So one thing we found out here is that almost all of these systems have small modules, which is a little bit surprising, because if you make an architecture for something, then you would expect developers to put stuff into these boxes. But some of the boxes really just contain a very small amount of source code. So that's an interesting finding here. And machine learning algorithms in general need data. And if we have a little data in some parts and a lot of data in other parts, things can become problematic. You could also imagine that entities, parts of the source code that is used by a lot of modules would be hard to map. And we could not really find good evidence that this is the case. We could also think a little bit about these mappings that we have used to evaluate our algorithms. Those are made by persons. So architects and developers have provided these to us, but that's a human doing something, and there is inherently bias in these mappings. So if you have two developers that do the same mapping for the same system, it is not clear that they will do exactly the same type of mapping. And we found this is an area where it's quite hard to find good data, because when you have a mapping, it's a lot of work to do, and it's hard to get several people to do the same work just to compare. So we have one system where we have at least two different developers that have made a mapping. And we could find up to 2.5% in disagreement here. And also, code is something that is evolving and changing, and sometimes developers need to do refactorings of their code, and this part can also be problematic for a mapper because the source code changes in some ways that makes it maybe more like something else in a separate module, but it also has some elements of the old module left. And developers are not always go all the way with their refactorings. So this also can make things harder to map. So that is some things to look out for. So to conclude, we have tried to improve the existing technique countertract. The dependency weight parameters are instrumental. We have invented this CDA technique, concrete dependency abstraction, to lift dependencies to an abstract level so we can combine them with the textual terms. And we have applied machine learning to incremental clustering by evaluating naive Bayes and constructed the NB attract technique. And we have provided an open source implementation of all this with the attraction functions, the experimentation framework, and a set of curated subject systems that other developers and researchers can use in the future. And some fun references. That's it for me. Thank you very much.
Thank you, Tobias, for the nice presentation. Very interesting. So now we leave the stage to the opponent so that he can make comments and questions to you. Please, Sebastian.
Thank you. Thank you, Tobias, for the presentation. That's, I think we met on many occasions over the last years and where we presented research, and it's very nice to see that the pieces and bits that you presented them now put together to a really nice PhD work. So, and it's really nice that we managed to celebrate this way in just 30 minutes. Really well done. So, if you don't mind, I would like to go through this discussion with you first by papers that you included in your dissertation, then move on to the general part about the contribution and the research method, and then conclude with an open discussion about where this might lead to in future work. If that sounds good to you.
Sounds good to me.
Okay, so I put a headline on each paper in the dissertation, and for me the headline for paper one was favor initial mappings with high fan-out. I mean, it's not that general, that's what your colleagues showed, but that's the main message that I took from the paper, that this could be, this guideline could be useful in general. And one question that I had after reading this paper, and that popped up again for several of the other papers as well, is about the randomization aspect in your experiments. So I think it's quite natural to use randomization when it comes to investigating the effect of initial sets, or to be more precise, to eliminate the effect of specific initial sets. But you also randomize the values of the parameters that the different attraction functions have. And I wondered what was the rationale for this. You could simply have, you could have done sort of a grid search or systematically combine parameter values instead of randomize this. Could you elaborate on that?
Yes, sure. So I didn't mention this in my presentation, and this is specifically for countertract then, I guess, because that's what the first paper is about. And we have these two parameters that are influence how this calculation should be done, really. And as you said, we choose to have them randomized. And well, let's see, this omega parameter, it is actually quite dependent on the size of the initial set that we use. So there is a general recommendation from the original authors here to increase that as the size of the initial set is larger and larger. So that could give some hints on where we should go with this one. The phi parameter is a little bit trickier because that one is about how much you trust the actual architecture, how much you trust these dependencies that are there. So for the first one, as we are not the architects of any of these systems, we simply did not have a clue on how to set this, and we wanted to collect a lot of data. So that's why we choose randomization for that one. And for the second one, well, it has some practical problems to try to make intelligent choices here, and it has to do with the parallelization of the different algorithms. To keep things as confined as possible and have less communication and less chances of error between different experiment runs, we opted to do randomization here also and just collect all of the data that we could find. But then, of course, these two could become really bad. And like you could find really bad numbers for these parameters that does not really make sense. So we actually do post-processing of these when we do our data analysis. So in that step, we try to find out good ranges for all of these parameters that then become unique for every system and also become unique actually for the different size ranges for this initial set. So instead of trying to solve that problem with programming code and running into problems with parallelization and trying to figure out a good schema there, we opted to collect as much data as possible and then do a filtering of that data.
Okay. I could imagine that it's interesting to look at one specific initial set and see how a change in these parameters affects one initial set or performs with one initial set and in another initial set. But right now with the complete randomization, you can't really ensure that given an initial set I, that you have all of the parameter combinations available, right? So if you have an interesting initial set, you can't say, well, I have a value for 5.9 and from the 0.5. You can't ensure that, right?
No, definitely not without looking at the raw source data, so to speak. That's definitely the case. Then again, we do collect a lot of data points here, so we try to combat that kind of like issue with having so many data points, so that, well, more or less, not every combination, of course, but a fair amount of every of these combinations should be covered, more or less.
Okay. Then you also say in the paper that we replace the manual mapping in Harmony with an article to map the single orphan and the automatic mapping phase to keep the process going. So you have the next iteration there, and the automatic mapping might find it all again. Is that the same? Did you apply the same process in paper 2 again? Because I didn't find any information about that in paper 2, or I didn't read carefully enough.
No, actually, we do not use any manual mapping in any of our future comparisons. So that is correct. That's this Oracle type of thing is not in the other comparisons. So they focus solely on the automatic performance of things. And I think the human aspect is something that we have not really looked into that much at all in this work. We have focused really on this automatic performance. How can we get that as good as possible? Yeah.
You also mentioned that certain random selections are better than going with a high 10 and you argue that there might be better mapping strategies, or that's the conclusion that you take from that. Now, after having written all the papers, do you think there's another potential reason?
Yeah, I think that the work done in this first paper, what it actually tries to what is actually kind of like happening here is something along the lines of these dependency weights. So it is a selection to select stuff that has probably good values in these dependency weights that is even better. And that is probably also why this way of doing things could not really be generalized. So we could not find a single type of good dependency strategy for constructing this initial set. And inheritance could indeed be utilized here, but the problem with inheritance is that it's not a very common dependency. So you have a lot more method calls, for example, between the source code entities than you have inheritance. But my guess is that we could probably focus a little bit on the inheritance aspect to create this initial set, and maybe that could increase performance even more. But again, I think it's a matter of also how much inheritance do you actually find? Can you find good inheritance in every of these modules? And especially for the small modules, I think it could be a struggle to do that.
Yeah, I was more thinking of maybe in these random settings where you got very good scores. Maybe with the cases where you map the small modules in the initial set, that you find notoriously difficult to map automatically.
Yes, definitely. And we also have this, there are some other entities also that are very, very hard to map. And these could also, if we get them into a fairly large, at least initial set, they will affect performance. And you can often see that a little bit in these curves that you have towards the end. It kind of like becomes a more distributed kind of performance. Maybe I can see if I can find an example here a little bit quickly. We should have something. Yeah, let's take a look at. Yeah, let's take a look at. Let's see what this is. F1 score. And yeah, so towards the end we see a little bit of more spread towards the end there, and this is the CDA comparison. Maybe we should take the final comparison. So they fan out a little bit towards the end, and in the end you can see it maybe more clearly also. And this is because of these hard to map stuff. If they have a tendency to become mapped by chance, then performance becomes good, and if they are not, then well, you have a high variability because there's not that many entities to map in these cases where you have something that is really has a large initial set.
Yeah, absolutely. Then I'd like to move to paper 2, which I assigned the headline "Optimizing Weights for Counterfeit." What I didn't add to the headline is that it's probably, it's not generalizable, basically. Not as a criticism on the research methods, but simply the fact that given the system, you can't really say, well, you optimize weights. So that's very interesting, but what would you say does that mean for practice? How can we somehow get a benefit from that for practice?
Yeah, I think we can take a look at maybe the nice table, right? With my little scribblings on it. So basically how we can use this information in in practice? Well, in this paper we did a comparison with other techniques that have tried to do stuff with different types of dependencies and valuing them in different ways. And the most interesting thing is that, well, most architectural reconstruction algorithms, that is, well, maybe the most popular topic to use different dependency weights, is that they tend to value method calls quite high, and in inheritance then so-so. And I think that's maybe something that we can work more on and try to understand why can we see this, and maybe we should value method calls less in these types of algorithms also. And from my kind of like own experience, well, method calls is the primary way to communicate between source code parts. So you make function calls or method calls, and well, naturally these will be abundant between modules also. And that is maybe something that we can take on. And also I think it's interesting to see that overall some systems are not designed with this overall thought about cohesion and low coupling for the implementation of it, and then it becomes really hard to use dependencies to do anything in general, at least. Then you need to have a more specific idea, and it could be possible that the developers knows, for example, that yes, we use a lot of inheritance and we implement interfaces within the modules. That could be something a developer could actually intuitively maybe know.
Do you think it might be worthwhile looking into types of systems? Like I noticed, for example, Chrome is again somewhat special as in other studies. And being a framework system, it might have like open-ended interfaces to that implementations. I mean, that might somehow affect this. Have you tried? But do you think that's an interesting line to look into?
Yes, definitely. I think Pro-M is an interesting case because it's so well designed, and it's well, this is business process modeling framework, and business process modeling people are maybe a little bit special in terms of being developers, and it's also an academic type of software also. So it's maintained by academy, and they are maybe use it in education, for example, as an example for design, and then naturally you would probably spend more time having it well for your students. But again, looking at Ant and teammates, they are very different types of systems. So yeah, I cannot really say that we can see anything in this data, at least, that there are certain types of systems that behave in certain types of way regarding this. Yeah, I think.
Yeah. I think in general it might be good to try to apply some, let's say, domain-specific knowledge here. The domain being software development, and the same for the method calls not being important, which I think rather means not being decisive in terms of whether they are internal or external. But if you maybe also look at sources and targets of method calls, like are these method calls specified towards interfaces where the actual implementation is somewhere else, then this might rather point to a method call coming from outside, you know. So I think this is a really great basis and might really benefit from looking with domain-specific glasses onto it.
Yeah. There's also another approach we could take here, and that is to look at maybe there are different weights of different types of dependencies between different modules. So that is also, now this is kind of like a generic for the entire system we have optimized the weights. So there could be specific parts between specific modules here that could be really interesting kind of like look at in more detail. Then again, this would, of course, if you want to set this in practice for a user, doing a mapping algorithm, you would then kind of like have a number of dependencies times the number of modules. So that would be, it's a lot as it is, but then it would explode more or less with the number of modules that you have. So for a mapping type of algorithm, I think I have my doubts that it would be practical, but from a research perspective, it could definitely be interesting to look at and see if there's individual differences between different modules or different maybe domains in general.
Yeah, I agree. And your third paper, which is essentially your tool paper, I don't have really questions about it. I just want to really express or appreciate this kind of contribution, because I think our community does not do that enough. Research, prototype, experimenting tools like yours that have this level of maturity and are open source, easily available. I think it's really great that you included this, and yeah, I think it's really good to show.
Yeah, thank you. It was fun developing it, and I will continue on it also. So it will live on for at least a little bit.
Yeah, I noticed during workshops that it's really important to. Yeah, great. So the fourth paper is then, I think, the main paper about base effect and the effect, more or less the heart of your thesis, I would say. And I think it's a very solid paper. What I found surprising here, ProM again stood out a bit, I think, and so I think, and the reason it stood out, why I perceived it this way, is that and the effect wasn't that much better as compared to other systems here. And that made me think, and I was surprised that you never looked at the degree of software architecture degradation in the system as a factor that influenced the results. What would you say about that?
Yeah, definitely. I think when things degrade, mapping will definitely become harder. We can probably agree on that. That if we have this super chaotic systems that I showed you maybe in the beginning, it will be very hard to map things, and because everything is dependent on everything else, and dependencies then becomes hard to use, and naming can also kind of like change over time. And when you refactor things, you make it work, but you maybe don't rename your variables or methods accordingly. Just, okay, this works now, let's move on. So I think in this hard mapping cases paper, we discussed this a little bit. But yes, I would probably say that ProM is one of the finer systems that I have seen in these types of workshops. Then I haven't really looked at the source code of all of these systems. I think mainly JabRef and ProM and Teammates that have been part of our Serocon workshop that have given a little bit of insight into it. I have no idea really for the other systems what the source code actually looks like and if there is a lot of problems and things in them. But definitely the heavily eroded system is harder to map. So that I think also this prompts the importance of trying to have conformance checking from the beginning, or at least as early as possible, because it will be harder for you to do conformance checking also then, because it's harder to map things and everything will become harder. And yeah, it's start with it's I guess like automatic testing. you want to do that from the beginning. You don't want to add a gazillion tests at the end, because then it will be not designed to be easily testable and things like that. So I think it's a little bit of the same story here. If you have a strong architectural vision and enforce that, then it will be easier to do this than if you don't.
But on the other hand, we as an architecture degradation community would like to convince practitioners to use it, and they won't throw their systems away. So there are existing systems, probably with erosion, and that's exactly where probably automatic approaches should perform.
Yeah, definitely, and I think this also ties into this, the problem of finding these hard to map cases. That's really an interesting area to continue research in, because we know that they exist, but we have no really good way of knowing which exactly they are. And well, while we tried to find some indicators, for example, looking at these small modules is definitely one strategy. So if you have a small module, then the human would probably need to map everything in there by hand, because it will be tough. Looking at these edge entities, we could see some indications that they are maybe problematic, but in general, will probably be a lot of false positives there. We have the entities under refactoring are also often problematic. So some parts of them change, some don't, and when will they cross in, for example, if you refactor something that's in one module and then it should be put in some other module after the refactoring, when does it actually cross this boundary, so to speak? And that's super, super duper hard, I think. So in those cases, I also think a human would be likely to be involved. But then just having a bunch of source code where you don't know this status really, then it's really, really hard to do good selections here.
Yeah, I agree. It's related to paper 5, you're already referring to cases. We talked actually already about one of the first question, which is about what could be ways out of the small module problem, let's say. Have you looked at what their responsibilities usually are?
Not that much in detail. We also have quite a liberal kind of like stance on what is a small module. So there's probably some differences between the different systems, but we have this. I know in Jabra, for example, we have this one small module is the preferences module with just a few entities in it. So that's probably a typical candidate for kind of like having small modules in this kind of like preferences or settings or things like that. Also have one module, I think called globals or something like that, with some global utility functions, and they just put everything into that part. And I think that could be maybe used, but then again, I also have seen systems where you have a lot of utility classes in a module. So maybe not universally, but it could be something to look into at least.
Might also help to go the other way around and be able to say which modules are definitely large, like user interface or logic.
Yeah.
They will hardly be small modules.
Yeah.
I think I will skip paper 6 because I've probably already spent way too much time. And just like to go to your Kappa and talk about the contribution and maybe a little bit about the research method. You put your research into this nice framework for design science, which is really nice, and you formulated your main technological rule developed as to automatically map from source code entities to modular architecture using machine learning and simple heuristics to create the training data. I think that is a very humble simplification of what the results of your papers, of your dissertation are. So the paper about this framework also states usually research takes existing technological rules, refines them or rejects them, in some way builds upon them. So how would you say, if you had to formulate 2 or 3 intermediate rules, what was the technological rule you started with? What were the intermediate steps that then got you to the final one?
Yeah, I think the first kind of like at least assumption that we did was this: the systems are overall designed with a low coupling and high cohesion. That's kind of like a little bit of the foundation also of the counter-tract method, and we thought that this would be something that we could more or less rely on. And for some systems, we find that this is indeed true, but there are also some systems that we don't really see this kind of like design paradigm or this technological rule, so to speak, that you should do systems like this. And some systems that, for some reason, is not really followed. So that's definitely something that, well, maybe it's not surprising, but it at least I thought it would be less obvious actually than what we could finally find in this dependency weights type of work that we did. Other types of technological rules, well, we have used a lot of different ways, especially when constructing our open source systems. I think there we have tried to make a lot of applied a lot of kind of like these design rules that we have, and to make it as well, both as reusable and as quickly developed as possible. So we try to use kind of like this model view separation and things like this. So basically a lot of these software design principles have been applied in this context. And I think that they have worked out fairly well. It has allowed us to create this software, and it works quite nicely. It's definitely not perfect, but we have been able to demonstrate it in a few different contexts and a few different ways of using it, with both performing experiments and doing this optimization algorithms and things like that. So I think that's basically the applied part of these different types of design technological rules for design.
Okay.
Yeah.
Okay. But when I said you formulated the technological rule very humble, and by that I meant that you could have said, well, please supply my NP interest in the future, and it seems to be better than anything else.
Well, I think you will. I think there will likely be better techniques, or I hope there will be better techniques as we go along.
Yeah, but for the time being.
Yeah. Well, at least if you focus on the automatic part, I think this is quite good. But then again, if we involve humans, it's it can be another type of challenges there, I think. So.
Before I like to discuss future work, just one more question about the concrete dependency abstraction, because it's also in the general contributions chapter. So if I get it right, you essentially add the term A method called B to a module. If there's a call between A and B, and you add that to module A as well as module B. So the same term ends up in both modules.
Yes.
Don't you think that this somehow influences the results? Because if A and B have nothing but this term, then the mapping or the scores for an entity to be mapped to them would be the same, right?
Yeah, so the idea is that, let's see if I can find my little example here. We should have an example of that, right?
Or in other words, could it be better improving the performance if you have a different term for A or B, say a method called B or a B method called from A or something like that, to distinguish source apart?
Yeah, okay. So I would probably say that it's actually already distinguished because you have the order in the A method called B. So we would then like to promote that if we add something to A that calls a dependency, much as this A calls B, that's fine. But we can also have something in A already. So when we add something to B, it would be a method call from that already mapped entity into this new B entity. So then we would actually have the same words generated there. So there is a directionality, really.
So I think my point is that without interpreting the term, you don't see the direction. You know, it's just a term, and what you do and the attraction function is to compare to see if terms appear. You don't interpret them. Here, the term appears for A and B without reflecting any directions.
Yeah, I think we did some initial tests also where we tried to infer more things like this, but that did not work out very well. But and also it's there are a lot of these terms because there's a lot of dependencies between the source code. So yeah, it's probably you're probably able to hypothetically kind of like create some situation here that it does not work that great in, but in practice there's so many dependencies. So in practice it's some other type of design that is needed.
Okay, so yeah, where do you see this, or how do you see this, in especially NVA attract, really used in a reflection modeling tool? I mean, now you have a very nice, obviously well-performing attraction function, but how do you support architects and developers with that and real too, in particular considering that the way of creating the architectural model fully is not always the way they work. They put one part of the model, map a certain part of the system to some part of the model, and then continue working, creating the other parts of the model. Can you just, tell me a little bit about what do you think how this could be best applied?
Yeah, well, I think first of all we must kind of like try to incorporate the human aspect here to begin with. So I think try to evaluate this more from a human perspective than this more automatic perspective that I have, and see a little bit what happens there. And I think the best approach that I have seen so far is probably InMap, that makes suggestions as you go along. And I think that would be an interesting idea to incorporate NB-Attract in that context and not just use this HugMe context that we have tried now, and see how good would recommendations be, how would a human, what kind of like steps would a human really take here to map something. But yeah, if the architecture evolves, and yeah, it's hard to say really what how a user would do this. You would probably have some parts of the systems that are quite easy to map, but again, finding these hard parts is hard. So yeah, it's a tough question, that one. How would we go about doing this? But I would expect at least the major parts of a model to be done, and then you try to do the mapping, and you would prompt the user to do some parts automatically. But I like the InMap approach here, where you make suggestions, and you work based on that. And you make this kind of like, oh, we show 10 suggestions or something like this. So we don't overwhelm a user with a gazillion suggestions or a gazillion mappings to kind of like approve, or if we want to go to the approvement step. And one interesting thing is also that we don't really know what the erroneous mappings mean. So that is also something that I find intriguing, at least, that, okay, we have a technique that tries to map something, but sometimes it makes mistakes compared to human mapping. What does that actually mean? Is the human wrong? Is the machine wrong? Is there some kind of middle ground here? So that's also something that I think is interesting to look into, and maybe even apply several different mapping techniques. Our focus here has been really to try to consolidate everything into one thing. Now I'm thinking more about, well, maybe we should separate everything instead and say that, well, the dependencies say that this should be in this module. The naming says that it should be in this other module. The source code itself says that it should be in this other module. What does the human says it should be in a fourth module? What does that actually say us? That would be also something that I think would be interesting to add to a tool, that you are doing something that is in line with what the machine says, or you're doing something that you're moving towards some other module now according to the dependencies. Is that really what you intend to do?
Yeah, I think an interesting question, and that's, I think, what we started with. Will that then really reduce the effort needed for mapping? If the human being needs to check recommendations constantly all the time, instead of doing it manually anyway from the beginning.
Yeah, definitely. So that's kind of like, at some point you probably want to just trust that the mapping is done correctly, or that the problems that you maybe find are not that severe. Or that you kind of like, when you see a problem maybe in the mapping, or you get some kind of follow-up problem depending on that, oh, this was actually not in this module that the algorithm thought, then you can make a correction. So it becomes part of kind of like the overall conformance checking flow, that no, it is actually conformant, but the mapping was wrong. So we can add that information now. But it's always this problem with false positives, I guess, that these types of tools are infamous for, and developers grow tired of checking false positives, so they then don't use the tools.
Yeah, that's a good point. So I think I'll leave the floor to the committee now. Thank you, Tobias, for an interesting presentation, for your research work, and for a very nice discussion.
Thank you, Sebastian.
Hey, thank you, Sebastian, for the nice discussion. So now we can invite the evaluation committee members to make some questions to Tobias. Raffaella, would you like to start?
Yes.
Please.
Okay. Thank you, Tobias, for your nice presentation. I'm not an expert in this specific topic, so I have enjoyed a lot reading your work, and so I have some curiosity and some questions. The first one is I would like to understand why you selected the reflection mode. If you say at the beginning that this is the least improper needed. But yeah, I think there are other approaches, so I was wondering why this one.
Yeah, well, it's there are kind of like these dependency structure matrices you can use, and there's also these rule-based systems, more or less. But it seems like reflection modeling is kind of like this. It has the approval of the industry. They don't really like to work with this dependency structure matrices because they look ugly or something like that. So in reflection modeling, you have the visual aspect of doing the model that's often already, at least maybe exists in people's heads, so that you have these kind of like modules and you have an idea of the dependencies. So that's basically why we went for it.
Yeah, and I think maybe because easier in a way to propose something that can be done in an automatic way if that goes another. But yeah, I understand your point. And then another question I have is about the experimental part. You selected a set of application and then you applied the method to propose on this set of application. So I was wondering if in some way this could influence also the result you have obtained. You mentioned something during your presentation and also with the discussion with Sebastian, for example, the fact that you have this small movie. But so the question is, do you think your results are general enough or are dependent on the application you have considered so far?
Yeah, that's a hard question also. I think to a degree we can at least generalize this to object-oriented systems in general, at least if we have some type of more modern object-oriented systems. So that's one thing I think is pretty generalizable. I also think that we have basically tried to find every system that we can lay our hands on during this time period, and there does not exist a lot of systems that we actually have a mapping for. So it's definitely an ongoing work expanding this. But I think there has been some work in architectural reconstruction. And I do not think that these results seem to be generalizable towards those types of recovered, implemented architectures. They seem to be too complex and too interdependent on each other, the modules in that type of system. Some higher level or some kind of like intended architecture or is probably needed. That's it should be this as I showed in the presentation, that type of architecture where you can at least see the boxes on a page and there's a moderate number of intended dependencies that you have and not these big balls of modules that's connected to everything. Those will be really hard, I think. Then we have a lot of systems in like lower level languages like C and stuff like that, and hard to say. I think it's declining definitely, the generalizability, especially if we have fewer types of dependencies, because then, well, if we only have function calls to use, basically, then everything will be communicating with function calls, and then it will be hard probably to do anything but try to follow like low cohesion, high cohesion, low coupling types of designs. And maybe that's also why in some in some work in architectural recovery. They use like C-type languages, and then they value function calls quite high, and then they get these pretty nice cohesive modules based on that.
Thank you. And just a curiosity about the way you need to conduct your experimentation. You have some part in which randomization is included. So I was wondering when you show the graph of what you obtain, are you conducting the experiment several times, or are you just showing something that you experiment for a long period?
Yeah, we can take a look at, I guess you mean one of kind of like these.
Yes.
Yes, yeah.
Exactly.
Yeah, so, well, as I said before, we rely quite heavily on being able to do a lot of experiments to cover a lot of the parameters, and especially this initial set of different sizes and compositions of the initial set, because there we can probably find a gazillion combinations, really. So there's a lot of experiments being done here.
Okay.
Yeah.
Okay. So of course, if you have very big systems, it will be really expensive.
Yeah, definitely. And I think the high performance computing cloud that we have here at LNU has been one of the most important actually parts of this, because I would have to wait another 20 years before getting the results otherwise.
Okay, and another thing I was, I don't know, maybe you say something, but do you think it is possible to apply this method also to recover, to go back to a good architecture? So apply it in the reverse.
Yeah. At the moment, I don't think so. I think it could be worth trying, but I don't. It could maybe provide some type of valuable insight, but architectural recovery seems to be sometimes the architectures that are produced, they are really complex, like this Hadoop and that I showed in the beginning. And I doubt that this kind of like technique used as a clustering algorithm would produce something like that. I'm skeptical, but yeah, it could be an interesting try. But yeah, I'm not too confident in that they would produce something that's really similar to what has been recovered in some previous studies.
Okay. So thank you.
Thank you.
Thank you, Raffaella. So now, Jim, would you like to make some questions?
Sure.
Please.
Can you hear me?
Yes.
Great. So thanks for a really interesting, engaging piece of work, Tobias, and finally pronouncing your name correctly, because I guess it's not that was used today. But I guess I've loads of questions, but I'm going to, yes, especially since Sebastian's comments, but I'm going to try and limit it to 3. The first one is about the CDA. Can we go back to that figure you were on page 30? Or it's marked as page 30, so I think it's about page 40.
Let's see. Whoop. 30 something.
In chapter 5, actually.
Okay.
Yeah, there's the example of the CDA for coding.
Here we go.
There we go. Yeah. So The CDA, and now I understand it works, the data you showed us shows it works, but I'm a bit confused as to why it works. Because, say, well, it sort of depends that A is not, small a is not the right module of big A. And if small a is not the right module of big A, then the person who did the mapping forgot to put in the intended dependency. So some part of that mapping is wrong then. Wouldn't it have been better if it was some way based on the intent dependencies? Because, you know, O could be, sorry, A belongs in module B could legitimately call B as well, or could inherit from B or whatever.
Yeah, this is a really good comment. First, so yeah, in this picture, there are no intended dependencies at all, just to make things a little bit simpler for this example. And we actually tried to, using the intended dependencies could indeed be a way to increase the model performance further. So we could extract the CDA dependencies based on the intended architecture. That's perfectly correct. And we actually tried that, but it didn't make any difference really. So there is an option in the tool to actually enable this, but it doesn't really affect performance. And my guess for that is that we will only have kind of like one of these, right? So again, I think it would be an interesting aspect to kind of like explode this homogeneous model that we have made into different types of models. So we could say that according to the intended dependencies as shown by the CDA and the intended architecture, you are now doing something that is strange. And we could also do it based on the actual dependencies. So in NB Attract as it stands right now, we could not find a benefit really of using these intended dependencies. So basically that's why they are not there. But I think if we do this explosion of the model instead and look at every part individually, that could be an interesting aspect.
So what you're saying is you could have small a inherits from small b approved, as opposed to small a inherits from small b not approved.
Yeah, sure.
Tag maybe or something like that. And that would be the explosion you're talking about.
Yeah.
Question?
Yes.
Yeah. Cool. I suppose the next question I have other questions from fantastic that talk about huge time. And I was really interested in a metrics question. And you know, which metrics? So this idea that you might do a pre-processing pass in your systems and figure out that you know the weightings to chapter in paper 2 should be such and such. But I was coming at it from a different angle. So I was thinking that the weightings in paper 2, that table of weightings that you came up with for inheritance was always one, you know, and that one, yeah. So my thought was there that you really need to look for the systems where, or you really need to look, sorry, for the roads where there's very different scores for very different systems. Because that sort of really informs what you might, you know, what systems might differ. So if you can find differences in the metrics of those systems, then that could really customize your weighting.
Yeah, sure. I think, well, our main goal here was that we wanted to see if things made a difference here at all, and then we had a feeling that it would, and as it turns out, it did. And then we found kind of like these interesting aspects also, but we haven't really gone that much deeper into why this is the case. So I think that could be a fruitful extension to this to try to see why does the related work weigh things in other ways, because we found some conflicting evidence here really. So it would be fruitful to do that. But right now, I don't really know why we have kind of like these differences between the systems.
Sure. Yeah, I suppose I've even shared shying away from why I'm sort of saying what's just pragmatically best. You know, if we can do a pre-processing and figure out that inheritance is best based on the fact that there's high depth of inheritance tree or something like that, or you know, that once so then if we find that pattern, we can look at the system and see, oh, high depth of inheritance tree, we've got to promote inheritance as a dependency of choice. So it's more pragmatic even.
Yeah.
Cool. So the last thing I just want to say is that I think all measures sanitize stuff. So, and I think that works against you in two places and for you in one way. So what I think works against you is that, you know, F hides the fact that, you know, a 0.1 measure in F is really, you know, a 10% increase in precision and a 10% increase in recall. So it hurts you there really because your tables don't emphasize enough. And I think somewhere would be great to put a little paragraph in there that talks to that. You know, a 0.1 F improvement is 10% of precision improvement down to 10% of recall improvement. And I also think that you made too little of the fact that, you know, you've got a figure that people should try and map. Because if I'm a software developer or architect who's trying to map the systems, and now I know that I only need to say 15% of the mapping for a really good shot at a highly precise rest of architecture. I don't want to do up to 20 if I know 15 is good enough. So I think those two places you understand yourself with. Would you agree?
Yeah, I think so. I think F1 score is well, it's good for comparison, but it's hard to take an F1 score and think about what does it actually mean in practice. So it's more of a research metric really than a practitioner type of metric. So for a practitioner, I would if I was to implement some algorithm, I would probably need to look at least the precision and recall separately. And yes, definitely, I think we actually have had a paper at Serocon some years ago regarding this. How much time does where do we have a breaking point between adding more stuff to the initial set or not? So we had some work regarding that. I don't recall it on the top of my head exactly what it was, but it is indeed kind of like the work effort saved is something that is important. That's basically what we are trying to do, reduce the effort for the human. So it would be an important aspect to look also deeper into how much time is actually saved here.
My final comment on that measure is that, you know, like your approach and the effect, it's very good. The precision is say 80% maybe, and you know when you're talking about maybe 100,000 elements or entities, that's still 20,000 entities that are imprecisely categorized, which is quite a, you know, in terms of real world information systems that are multi-million lines of code and stuff like that, that is still an issue, I suppose. Yeah, definitely. I also think that we have not really experimented with this threshold of when to map and when to not map. We have just, for MBA tract, we have just set it as at, if you have a single entity above 90%, then we do the mapping. So you could increase that to 95% or 99% or something like this. That could improve the situation also, but we haven't really done any experiments in that department really. So yeah, yet another parameter to play around with, I guess. Yeah, thank you very much.
Yeah, thank you.
Thank you, Jim. So now, Miguel, please, we finally move into the room from a face-to-face discussion. All right. Tobias, thanks very much.
Yes.
Take a presentation.
Oh, you should have a mic, I think, or a box.
Sure. Yes. I have one of questions actually, so they're not going to fit into today, I'm afraid. We have to find some time offline.
Definitely, yeah, definitely.
One of the first questions I have is about better to use this one.
Yeah, it's more like a told me.
Yeah.
One of the first questions I have is on the scale, though, and mostly the scale of the systems of the architecture. If I look at the and quickly browse where I find it, it's at table 3.1, my page 17, but you might have renamed it.
Yeah, let's see if I can. I think we have 33.
Section 3.4.
Oh, here maybe. Yes.
So my interpretation is that column 10 denotes the modules in the architecture.
Yeah, the number of modules in the architecture.
Right. So if I look at below n, you would have 4.
Yes.
I think that's a very small number for architecture.
Yes. Definitely. I agree.
So, okay, I'll repeat now that I think it's good work, but I'm going to ask 40 questions again. I don't think 4 is an architecture.
No, yeah, I think I could to some degree agree there that this is basically the source code, let's say components or something like that. This is basically the jar files of Pro-M that has been mapped in this way by the architect. So it was made by the architect, so it's in some way an architecture.
Okay, well, one thing that I'm going to come back to is, so I've been looking at architecture and implementation. So my conclusion is neither of them is right. Yeah? The architecture is never right, but neither is the implementation, right? And you're actually in the middle. Yeah? So whenever you find a mismatch, you always need to figure out, is the implementation wrong or is the architecture wrong? It seems you tend a bit towards assuming the implementation is right.
Yeah.
The architecture is right.
well,
anyway.
Yes, we are at least assuming that the mapping is correct. So that's one of the assumptions that we do, that the mapping is correct. But yeah, we cannot really. We know that the implementation will, in some cases, be eroded, for example, and be strange and odd. So yeah, that's indeed true. And I think this would be very interesting to see if this can more or less be used as a conformance checking method. So if you have the human mapping and if you have the machine-made mapping and they don't agree, there's something wrong here.
So I understand that you assume that the mapping that you get is right, but then my suspicion is that the people that made the mapping didn't check say the sanity of the implementation.
Probably not in all cases, at least. I think since I have not been personally involved in all of these recoveries, I think the one that has, from my perspective, the most solid mapping and is actually JabRef 3.7. There we had quite a nice session with a developer / architect that basically, yeah, he went through the source code pretty meticulously, and it took a long time to do. But and that was maybe also one of the inspirations for this work, because, well, it was not super exciting to be in that session. It was interesting to a point, but yeah, then it was very long and a bit tedious at times.
So maybe to the picture that is the architecture of, there's one picture in there.
Yeah, yeah, probably. I have it, probably. And you don't see, no, you don't see my, yeah, you see my screen there, right? Oh, no, we should have in the beginning, right?
Yeah,
so this one.
So this is that it has six modules, 6.
Yes.
Can be. They are part of the music engineering. Logic is model engineering. And model is model engineering. And goals and preferences probably is one. And CLI, I'm not sure. So I would tell that you already have 3, say, components, GUI, logic, and model that you could use for any system.
Yeah.
So if you say, okay, I need a starting point, well, here you have one, independent of whether anyone supplies you with a starting point, right? Because it's almost a reference architecture, user interface.
Yeah.
And you can have starting names. But I would argue that orphan systems are hierarchical. There's actually levels of nesting. So how is it fitting the approach?
Yeah, I think for the architectures that we have in this work, there's no really hierarchical parts of kind of like components or modules inside modules and stuff like that. That was actually also a little bit surprising to me, that this was not utilized more actually in these architectures. I think we have used that part when we do our keyword stuff for the fully automatic mapping. Then we highly utilize that. All of these systems tend to be in some way mapped by file structure, or has at least traces of file structure in this type of mapping. So that's definitely can be a very important piece of information to use.
Because you said use barcode.
Yeah.
So you throw away the entire file structure?
No, the file structure is still available, because we also use the file names. So we have the full path of every file. Yeah. Yeah.
Okay. As I said, I need to make a bit of selection. But one of the thoughts that came up is you've shown these graphs, and they show the F1 performance, I suppose, right? And then at the end, you see this widening again. And I suppose the point where it starts widening can be the point where you start dealing with the difficult cases. Right?
Yeah.
So it seems that from your graph, you can determine when you start dealing with difficult cases.
Yeah, that could be an interesting way to at least try to detect if and when you have starting to come into this, because you could, if you have a good mapping of things, and you have this evolutionary case of mapping, you could see that, all right, if we just reduce the initial set, we have a pretty stable performance, but then when we add things to it, and maybe if we add these certain files, then we could see that, all right, this file seems to disturb the performance if we perform a lot of these experiments. Yeah, so that could be a really interesting approach to pinpointing these elements. Yeah. But it would assume that you have a pretty large set of stuff mapped already. And you always have the performance issue, because you would have to do a lot of combinations of different sets to find these files, I guess. But you could possibly have some intelligent strategy there. You're just removing one and do mapping and see what happens.
And you can get intuition what's the size of the starting map that you need. Do you know? I mean, if you have, on the table, we can see you have like between 6 and 20 architecture components.
Yeah.
How large does your starting set?
We can. I think actually we have had a paper on this on Serocon, and not me, but some other people have had that. I think we are. Let's see. We will go here and we will take an overview. Let's see. Yes, let's see. So, hard to say, of course, in general, but 10% at least, I would say, then we are probably on the safe side. Maybe not for Sweet Home 3D here, but yeah, between, let's say 15%, that's roughly what you would need for the initial set. Then you are probably pretty good to go.
And then it's 10% of the implementation.
Yeah. And it's also kind of important that we have a good distribution among the modules. So not 15% in one module, because then it will not work that great.
So while we have these graphs on the screen, do you think that the spreads for particular approaches could say something about the quality of the architecture?
I think, for example, for the orange one, which is counter-tract, that has the most spread, definitely. I think it seems to be more, probably more sensitive to these different types of dependencies that we get. Then again, it is also this matter of finding the good parameters that we discussed a little bit with Sebastian. So it's hard. I think it's hard to tell something about the architectures per se.
Okay. So if I understand the algorithm right, you try to rank files, and you see if they match, but if they're hard, you push them back into the orphan set, right?
Yeah, if we cannot decide, find a good kind of like, the idea in Hugme is that you should have some way of deciding that, okay, this attraction is good enough.
Yeah.
And both counter-tract and these two IR attract and LSI attract, they kind of like try to find an outlier. Is one of these attractions an outlier between the others? And then they do the mapping. For naive Bayes, we use kind of like, since it's a probability, it's easier to interpret, so we just set 90% there.
Because in principle, you could end up with a bridge that you cannot make at all.
Yeah. So low recall, so to speak.
But the algorithm does assign them in the end? Or?
Yeah, it doesn't do anything with them. It just leaves them as it is now. In Hugme, it would be the user that is prompted to do this. And you can use it. No. We have not done anything about those in the later parts. I think Crystal et al., they proposed that you should use the attraction as a guideline. So you should propose the one with the best attraction first, and then in a descending order.
Okay. And then you have the graph in figure 2. I have it page 235. It's one of the papers. It's essentially comparing the F1 score for the different cases.
Could it be this one? Okay. So it's let's see. Which paper was it in? Was it in? No, it's not that one either, right? Paper 2. Okay.
Paper 2.
Okie dokie.
It's in the last chapter.
So it should be right here, right? Let's see where it could. There we go.
There you go.
Ah.
There you go. So we've made some interesting remarks. We said, okay, somehow we need to deal with systems in different ways because the same metrics don't work for all systems. That's one thing. So I think that could be one reason why you get different performance, right, for different systems here.
Yeah, this is kind of like the different types of dependencies, and maybe I'm coming back to the kind of like the same things here. If we, for example, take a look at JabRef, that's I think is quite well designed. We have not a huge difference between these the performance of the optimized weights versus the uniform weights. Really, just putting everything as one would be quite okay. And probably not worth the effort to try to find out these optimal weights in a good well-designed system.
I have an alternative explanation. I would claim, I'm not going to claim it, I'd like to hear your view. It seems that it might be explained by saying the projects that have the best performance are the ones that have the smallest number of architectural models. And there's a fairly reasonable explanation from a machine learning perspective.
Yeah, this is not at all the machine learning part. There's no machine learning involved in this part. So, but that would be indeed the case. I also think, in general, if you have fewer classes in machine learning, it would be easier by chance just to pick it right.
Yeah.
So, yeah, yes, definitely.
Okay. Let's see.
I would be correct in 1/5, or was it 1/4 of the cases in Pro-M, just by throwing my darts.
Yeah. This is a short question. Would you consider ownership of the file to be a potential predictor?
Yeah, I think that could be an interesting aspect. I think overall, kind of like using more information from a source code repository would be super interesting. Ownership of a file, if several people have been hacking at the file, how much it has changed over time or recently, and metrics like that would be really interesting to look into. But maybe not for the mapping per se, but at least in a conformance perspective, I think that could be done. Persons, I think, could probably be interesting from a mapping perspective, because probably the same people would work in the graphical user interface. That could be a reasonable assumption in some cases. Yeah.
All right. Thanks very much.
Yeah.
Thank you. So now we give the audience the chance to make some questions, either here in the room or people joining from Zoom. So for people joining from Zoom, you can either raise your hand or just drop a message in the chat, and then I will read the question to Tobias. Or people here in the room, if you want to make a question, just raise your hand, and then I will come. Yes, nice to hear.
Thank you very much, Tobias. Also joy.
Yeah, I see you're smiling, so.
I have actually one question and also a question that might be more of a. But let's start with the question. Time as a factor. You talked about file structure, like file names and everything. And I'm just thinking out loud now that many of these projects might be spanning over actually long periods of time, maybe 5 years. I'm just guessing now, but shouldn't this affect also, like, something that happened 5 years ago might not be relevant today in terms of architecture choices and dependencies, etc., etc.?
Yeah, sure. I think time could be an interesting aspect to use, and also, at least when trying to figure out an architecture of a system, it's often in the beginning that you have this strong vision of this is how it's supposed to be, but then it can decline over time. So it can actually be beneficial to try to do a mapping of an earlier version of the system, and then you get an initial set for that, and then you can see if these files are still present in the most recent version of the system. So I think, time is an interesting aspect, and it ties into this concept of repository data mining to extract more and more information from our development, really. In my case, we have really just snapshots of stuff, except maybe for YabRef, where we have 2 versions. But yeah, it's hard also to make assumptions just based on 2 versions. But yeah, definitely.
Yeah, and other thing which I know you have also explored a little bit is the GPT-3 approach. Like you have these tools now that you can install in Vision Studio Code that help you with coding.
And it's not far-fetched thought to think that this might be also something that could be implemented, what you have been doing, as like maybe you get some kind of prediction on what you should call your class or library or where it should fit into the structure.
Yeah. I think there are tools, for example, JITAC, that gives developers at least just-in-time feedback as they program, that they are doing something that is wonky or wrong. But this can definitely be extended to introduce more things like, well, you should probably use these variable names because the other classes in this module uses this type of vocabulary, to try to keep things more cohesive. And also you could, I think especially in refactoring situations, maybe speaking for myself, mostly you kind of tend to fix the functionality and move the functionality, but not really rename variables and stuff like that, because yeah, it works, so let's move on to something more fun. And there's always the risk that the vocabulary of a module would then just dissipate into nothing and be really incohesive. So making suggestions and even maybe prompting developers to more carefully refactor and name things could be an interesting aspect also. And again, it's a little bit about this chopping up the homogeneous model to different parts again and try to do something there.
So thank you very much, Tobias. I also have a short question. So how can we programmers make use of this? How far away is it that can be analyzed by your system?
I think you probably, since we are gearing it more or less towards the reflection modeling situation right now, you probably need to have an ambition to use reflection modeling first. And then you can try experimenting with different types of mappings. But I also think that maybe you can just play around with this and see what happens with it in a code base that you are familiar with, and see if you can find something interesting. One of the reviewers of the JOS paper that we did actually contributed also with Commons imaging, and he did exactly that. He was the developer for Apache Commons imaging, and he wanted to try this and play around with it. And I thought it gave him some interesting information and contributed with this mapping also. So I have no concrete kind of like, you should absolutely do this and then you will get this type of things. But yeah, play around with it and see what happens. And I think one of the most interesting aspects in the tool as it stands now is that you get a list of these, every wrong mapping, you get a list of them, and you get that in order of priority, and then you can take a look at why is this one always mapped into the wrong module. That could be this prompt to go investigate that piece of source code again.
Okay, so have you used this on your own, on the tool itself?
No.
Okay, that is.
Yes. I don't dare to do that because then I have a lot of work to do probably.
So thank you, Tobias, for
Thank you.
this interesting talk, and you nailed it twice at once.
Woohoo!
So I just want to start with this figure that Michel discussed. I mean, I don't want to comment, maybe also want your view on it. So it's the strong hypothesis that Michel made is so systems with small number of modules tend to perform higher, but that can be one case. But another strong assumptions can be made on this figure is systems that has higher number of modules, they have a high variability, so they have higher intercurrental range. So what do you think? What's the possible value there?
Yeah, it would be good if we could just compare these kind of like, so maybe we should take a look at, I think, the performance of the actual mapping, right? Because that was still the oh, let's see, it should be somewhere here. Oh, this one is probably the one that we want to discuss. So this is the performance of the actual mapping, different types of mapping algorithms, and bigger systems, higher variability.
Because T-meters and C-image, I think these are bigger systems. And then, since you opened up this figure, and I also have a related question about this. So this is the comparison of the performance, but then is the performance by NB trucks is statistically significant?
Yes, it actually is. Then, from the statistical point of view, it is quite easy to get significant numbers here because we do a lot of samples. So it's more or less not guaranteed, but it's quite easy to get significant results because there's a lot of data points. So any deviation would probably be more or less significant. At least there are some exceptions between the algorithms, I think. Yes, but there is a table with I think we didn't even bother to write the exact.
Yes.
Yeah, the exact. We wrote the exact test, but we didn't bother to write the p-value for every one of them because it was very many 0 digits to write, and yeah, one or two cases. I think it was maybe between the LSI attract and some that wasn't significant, but that was marked at least in the table.
So I also have two more obvious questions, maybe. Just thinking linearly here. So you experimented with multinomial naive-Bayes, I guess, but did you also experiment with other algorithms, or why did you put multinomial naive-Bayes in this particular case?
Yeah, so we rely on Weka, the Java machine learning library. So we basically tried all of their classification algorithms in a very limited data set, I would actually say. And we saw that, well, naive-Bayes seems to be the one that performs well. Let's go with that one. So there is definitely a possibility that some other style of decision trees or whatnot could perform quite well. Quite frankly, I think that spending more time and tweaking, for example, IR attract or LSI attract could actually be beneficial. The paper that those are built on is quite, well, it's hard to know exactly what they did. So we have kind of like made our best efforts to follow how we think that they did it. But I think if we spend a little more time here, we will probably increase the performance of them. But I doubt that it will be such a massive performance increase, really. And from my own standpoint, I think naive-Bayes was the easiest one to understand what's actually going on here to a certain degree.
In general, multiplication is also better performance. So maybe in terms of performance or how quickly naive-Bayes work, maybe better than
Yeah. And we also have this, we wanted to work on small sets also, small data sets. That's also a thing that where naive-Bayes is fairly good.
Yeah. And another point I wanted to discuss is about your genetic algorithm. So I think had many possible ways to configure or optimize, like number of the size of the initial state, what type of selection you make, what type of crossover you choose. So is there any way to optimize these decisions, or you pick randomly picked any crossover method or any selection method or any size of the initial state?
Yeah, okay, yeah. We can maybe, I have a slide about that, right?
Yeah.
Oops, oh, how big?
I think it was about
Yeah, it should be here. Here we go. Plop. So yes, well, there is a lot of kind of like convenient choices here, basically. So we want to have a reasonable representation of different sizes of initial sets. So we okay, 10 will be good enough. But we want to have them also, the composition of these is random. So random composition, but we have kind of like these fixed sizes to get a broad sense of the performance. It could be interesting to hone in on maybe the evolutionary case where we have a large initial set, or the revolutionary case where we want to map something from scratch. That could give differences in the dependency weights. And then basically it's things that worked the best. That's basically how it was done, given also reasonable time frame and resources and things like this. So it's always a couple of trade-offs you need to do.
Because there are lots of choices for selection.
Yeah.
Maybe just one final comment. So I think you only consider the bytecode, right?
Yeah.
Not the source code, the real source code. So because when you are extracting semantic information from the bytecode, let's say identifiers or other things, other information, maybe if you could complement this bytecode with the comment, which might have more relevant information, it would enrich or improve your model. Right?
Yeah, definitely. It's the comments are definitely a source of information. We did some initial tests, and we could not really see any great benefit of it, at least. But it's definitely an area where you could spend more time, I think. So yeah, comments are, I think, interesting. They can be both good and bad, I guess, because sometimes they are not maintained in the same way as the source code. So it could be a double-edged sword, but definitely something to look further into.
Yeah. That's
yeah. I think InMap has valued comments in their suggestions, and there it worked quite well. So maybe it's something that we should continue with.
Thank you, and congratulations on that.
Thank you.
Any other questions from the audience here on Zoom? No? Then I also have a question. Sorry to be.
Oh, no problem.
Oh, that's more a curiosity. I was just wondering about, the differences that you had in the results. We know that nowadays, for developing software, we usually rely on frameworks or platforms or whatever. So could it be that, some of these softwares that you just analyzed are based on some platform that force the developers to follow up sort of architectural style and others? I guess, Hunt, I think that, they just seems to be then more spaghetti coding than
Yeah.
architected software.
Yeah,
for
yeah,
the results.
yes.
Could it be? I mean, that's
I think for the systems that we have in our data set, frameworks would play a role, but I don't think it's that super important of a role. I think, for example, we could see in Jabra, for example, that's a typical desktop kind of like application. You have graphical user interface. I think more importantly, I think this information is missing from the architecture. I think we should try to spend more time also mapping up these modules or components that are outside of our system and how we depend on them. I think that's also an important piece of information that we should be able to use in some way, at least from a conformance checking perspective, that you're doing calls to something that is outside of the architecture, but you shouldn't really do that because you're now calling the Java FX library directly, but that's not kind of like part of the architecture, so it won't be really checked. So I think adding this, what kind of like layers or modules are you trying to encapsulate or protect the code from really? What you kind of like add modules or layers as abstractions to your particular domain. I think that information is in large missing in these architectures completely. And I think that would be an interesting and important part to actually add to this.
okay. Thank you very much.
Thank you.
So if we don't have any other questions, then I think we could close the session for the moment. Me, Michelle, and Anna will move to another room and join the evaluating committee for the final decision. So you can wait here.
Yes,
for
okay.
a few minutes.
Yes.
So we'll come back.
And I can take off this mic and headset, right? Oh, thank you.
en del av ungefär att teorin en timmes tid testade.
Oj.
Ja, den var en timme. Det var så på gränsen att vi fick säga till ordföranden att man var.
Ja.
Men det var en personlig vendetta bakom.
Ja, men alltså.
Ja, det var helt gränsgående. Men hon gjorde det så.
Där har vi dig.
Ja, precis. Spring!
Jo, jag får sagt att jag vill absolut. Man vinner ju med huvudet. Och sen kommer de bara annansa det och sen så klick i skål.
Han har gått vilse i byggnaden. Det är första gången han är här. Han lär ju vara... Oh. Kan ju vara så att de är på ingången nu så smått. Nu har de ju dykt upp där. Ja, precis. De har gått upp och ätit tårta. Så, kommer de den vägen? Jag tänker inte dra på med de här plågoredskapen igen. Sennheiser. You can use this one. It's you don't need to wear it, I guess.
Yeah, very cool. Yes, we've had a fairly brief discussion, I would say, where all of the members of the committee shared their views on your thesis and the details. And there is a unanimous decision.
That's good.
It should be awarded. There's a few things that I would like to repeat out of the discussion. One of them, starting, is a good presentation and nice slides. And the other thing regarding the thesis is that there's a clear story and there's actually a good connection and good cohesion amongst all the chapters indeed. The committee is convinced that you have contributed to the state of the art and that you've contributed novel insights as well. We also believe that you have demonstrated to satisfy the criteria acting as an independent researcher in the academic community. So rounding all that together, the committee is advising to award the degree.
Thank you very much.
Next step to someone else, I think.
I think, so yeah, I think that we now conclude. Congratulations, Tobias. Thank you, everybody, for joining this wonderful day. So here we have a new PhD.
Thank you.
Congratulations.
Thank you. Thank you very much. Thank you.
Now it's gin time.
Yeah, I wish.
Yeah, I really
Yeah,
like it.
yeah. Cake and refreshments, right?
Yes.
Yeah. So please. Yeah.
Where to?
Yeah. Up in the fika room.
Very sorry, people that cannot